All right, section 3.3, maximum and minimum values. All right, as you can kind of think about it, the global economy, businesses are always trying to minimize their waste and maximize profits on their investments. So it's very important to realize how can we find maximums and minimums. All right, so 3.3 looks at this purely mathematical right now, and later on in the chapter, we'll talk about it more in real life. All right, so first we're going to do is we're going to define some terms. It should be pretty obvious. Okay, and the first is the absolute maximum. The absolute maximum of a function on a set, or it is the absolute maximum on a set, if the f of c is greater than or equal to every other single f of x value for all the x's in that set. Okay, minimum the same thing except f of c is the lowest. It's less than or equal to everything in the set. Okay, so you could have more than one maximum or minimum if they both have the same y value. All right, these are the absolute, means they are the lowest or the highest. Together, we just want to talk about absolute maximum or absolute minimum without actually using the word maximum or minimum. We say absolute extremum because the extremes. And if we have more than one of them, we call them extrema because that's the plural form of extremum. All right, so let's look at a couple examples here. Example 1, locate any extrema on the following. Okay, so we're looking for maximums and minimums, absolutes that is. All right, and first off, we have x squared minus 9 on the interval negative infinity to infinity. All right, in fact, a, b, and c all deal with the same function, but just on different intervals. So we can kind of discuss that and see a little bit what's going on with what absolutes actually are. All right, so on this one, if I go from negative infinity to infinity, it's not drawn here for you. All right, but there's actually arrows that are going up. So this thing actually grows forever and ever both directions. Okay? We'd say the limit as we go to negative infinity to the left is infinity because it's going up. Infinity as we go to the right, it's going up, so that limit is also infinity. So there is no absolute max. No absolute max. All right? But there is an absolute minimum. Okay? This point right here is the absolute minimum. Okay? And the way we would write that for this one is the easiest way to talk about it is to say, you know what? That happens at 0, and so the f of 0 is equal to negative 9. Okay? The absolute minimum is negative 9. It occurs at 0. So sometimes you'll see some test questions where it says, where is the maximum or where is the minimum? That's the x value where it happens. The actual maximum or minimum is that y value or that function value there. Okay? So that was pretty easy to see. This one had a minimum, but no maximum. All right, let's look at this one right here. Same function. We're just looking at it between negative 3 and 3. All right, notice negative 3 and 3 on this one have parentheses. That means negative 3 and 3 are not included in the interval. Okay, I don't know if you can tell on your paper, but there are open circles right here at negative 3 and 3. All right, well, obviously, just like the first one, we can tell that it has a minimum, absolute minimum, at the same place. F of 0 is equal to negative 9. All right, but it might be a little confusing here to talk about the maximum. Okay, so definitely it looks like there's a stopping point. Okay, it looks like that stopping point is a y value of 0. All right, but since there's an open circle, that means the function actually never goes there. Okay, we can plug in a 2.9 and a 2.99. Okay, and those have values that are really, really close to 0, which would be a maximum. But however close you get to 3, 2.99999, you can always get infinitesimally closer, which will make you a little bit higher. Very small, a very small margin, but it'll get you very high. Okay, so since numbers are continuous, this actually never reaches a maximum. Because no matter what number you plug in, you can always get a little bit higher than that and get between that high number and 3. You can always get a little bit closer. So this one also has no absolute max. All right, now that changes when we do the C part. Okay, the only difference between B and C is that we have now included -3 and 3 in our interval. Okay, and so on this one we have the same absolute minimum as before. All right, that minimum was that f of 0 is equal to -9. All right, and now since we actually have those points right there, we stop at -3 and we stop at 3. Those are going to be maximum values. All right, so we'll have maximums, or maxima, I guess I should say. All right, at -3, the maximum is 0, and we have another maximum at 3, which is exactly the same y value. And for you to have 2 absolute minimums or 2 absolute maximums, those y values must be the same. If not, well, then one's higher than the other. All right, let's look at this one. I got the function 1 over x on the interval -3 to 3. Okay, so I stop right here and I stop right there. All right, well, what is the highest this thing goes and what's the lowest this thing goes? All right, well, if I'm coming from the right, this thing goes down, but actually it does what? It goes down forever, okay? There's an asymptote here, a vertical asymptote, at x equals 0, and this curve goes down forever and ever and ever. That limit, as x approaches 0 from the left-hand side, will be a -infinity, okay? So there is no minimum, okay? It keeps on going down forever. However far you go, you can always go a little bit lower, okay? Same thing's true when we're coming from the right-hand side. As you get the limit, as x approaches 0 from the right, our y values are increasing without bound. They're going to infinity, so there is no absolute maximum. All right? So we had the first example where some of them had a minimum. Well, they all had a minimum. And then only one of them had a maximum. And this one has no max or min. All right, this brings us to this theorem right here, the extreme value theorem. All right, a continuous function f defined on a closed, bounded interval, AB, attains both an absolute maximum and an absolute minimum on that interval. All right, so the key things there, it's a continuous function, all right, and it's closed and it's bounded. All right, so this previous example, I didn't number it, it was bounded, it was closed between -3 and 3, all right, but it was not continuous. All right, going back to example 1, this one was not bounded. We went both directions forever and ever. This one, we bounded it between -3 and 3, but we did not close it off, okay? So we were not guaranteed to have both. However, on this one, example 1c, we are closed, we were bounded, so we were stopped at -3 and 3, and we actually had points there on the edges, and so that guaranteed that we're going to have both an absolute max and an absolute min. All right, you can thank a guy named Bernard Bolzano, who discovered that, or proved this, not discovered, but proved this in the 1830s. He was actually a mathematician, a philosopher, and a Catholic priest who was pretty liberal and got exiled from his home country of Bohemia. And was not actually allowed to publish stuff during his lifetime. But most of his work is known posthumously. But Bernard Bolzano proved this in the 1830s. All right, so let's look at this one right here. Again, just looking at a graph. All right, we'll get to a point where we can just look at a function, but not right now. All right, so this is the same function that was our previous example, 1 over x, but now we've closed and bounded it between 1 and 3. All right, well, 1 over x is not continuous over everything, but is it continuous between 1 and 3? Yes, there's no asymptotes between 1 and 3. That asymptote happens over here at 0, which is not in our interval. So it's closed and it's bounded. So by the extreme value theorem, again, it's pretty important, EVT, extreme value theorem, we're guaranteed to have an absolute max, and we're guaranteed to have an absolute min. Okay, and graphically we can see that pretty easily here. The absolute max is the highest point, and that happens like what looks like at 1. We plug it in, 1 over 1, yes. Absolute maximum, f of 1, which is 1. All right, and our absolute min is the lowest point on the graph during that interval. That looks like this happens here at 3, at the very end of it. And if we plug that into our function, we know exactly where that is. Our absolute minimum, f of 3, is, in fact, 1 over 3. All you have to do is plug it in to 1 over x to figure out exactly that value. All right, so before we can determine how to locate absolute extreme of a function without looking at a graph, that's pretty easy if you look at a graph, we need to consider another type of extreme. Okay, local extremum. Okay, they might not be the highest over the entire set, okay, but they're highest in their little area. Okay, just like the hill, if you're driving down 51 up next to Mama Hamels, okay, that's the highest hill, it's the highest place in its surrounding area, but it's definitely not the highest place in the state of Mississippi or in the entire world. Okay, so local maximum, okay, an f of c, or y value, is a local maximum of a function if it's bigger than or equal to all x's in some open interval containing c. So if I can find some open interval, okay, and it's the max, that's the local max. Local min, same thing, it's just at the bottom. Okay, graphically, basically what happens is where the hill is, that's the max, or where the valley is, that's where the min is. All right, so let's look at these. Graphically, let's see what's going on here. All right, we can definitely see a valley here. Here's a local minimum. Okay, here's a local maximum. Here's a local minimum, and here's a local maximum. They're the high and the low points on the interval. All right, what's important about this to look at is to think about what's happened on the derivatives of these points. Okay, right here, that derivative, which is the slope of the tangent line, is 0. Up here, we have the same thing. That tangent line there, the slope is 0. All right, but the ones on the right-hand side, okay, we actually have cusp there. So this function is not differentiable at c and d. All right, but it definitely reaches a low point and a high point. So there's still maximums and minimums, or maximas and minimas, locally that is. All right, so the derivative there is undefined. So we have sometimes where the derivative is 0 and sometimes where the derivative is undefined. All right, let's look at these. Can we locate any local extrema for the following functions? Describe the behavior of the derivative at the local extrema. Okay, I've put the graph here for us to look at. Okay, let's see if we can do this without looking at the graph. Okay, I know I can't hide yours, but I'll hide mine real quick. Okay, so I can't look at them. All right, but I can use that information on that previous graph to help me out. All right, it looks like our local maximums and minimums occurred at places where the derivative was 0 or where it was undefined. All right, so it becomes a calculus question. All right, to find where this local maximum or minimum occurs, we just find the derivative. All right, so the derivative of this is going to be, derivative of the 9 goes away, and we say this is what? Minus 2x for our derivative. All right, and we want the derivative, let's see, where is this derivative 0? All right, this derivative is 0 when x is equal to 0. All right, so we have a good suspicion that there's a maximum or minimum at 0. Well, which one is it? All right, well, in this one, if we just think about it for a second, we got x squared, which is a parabola, but it's negative, so it's what? Downward facing. So we're pretty sure, even without consulting that graph, that we have a minimum, or excuse me, a maximum, a local max, at least, f of 0, which we plug that 0 back into the original function, we get that y value, which is the local max of 9. All right, now let's look at this absolute value. Well, let's think about the derivative. I don't think we ever learned how to find the derivative of absolute value. All right, but we know what it looks like, yes? Even without seeing the graph, we know that it looks like a V. All right, and the bottom of the V is at 0. All right, so we know that local min is going to be f of 0, 0. All right, and I guess we need to answer the other questions. The derivative on this one is undefined, so an undefined derivative at that minimum. And here the derivative is 0. All right, so a little exploration there. All right, which brings us to this definition right here, and Fermat's theorem here. A critical number of a function f is a number c in the domain of function f. Okay, I know the f's a little cut off there, for which the derivative is equal to 0 or the derivative is undefined. Okay, so those places we just found where the derivative is 0 or the derivative is undefined, that is called a critical number. Okay, and I'll probably abbreviate that C in. All right, and that brings us to Fermat's theorem. All right, we have a French mathematician named Pierre de Fermat, and he was actually not a mathematician by trade. He was a lawyer. He just did maths for a hobby. But they sometimes called him the Prince of Amateurs because he was not a professional mathematician, but he was extremely smart. In fact, in one of his textbooks, he came up with this theorem and said, ooh, well, I could prove it, but it's not going to fit in the margins. And so we think he could prove it, but nobody else could prove it for 300 years. It wasn't until 1995 when they proved Fermat's last theorem. All right, that's not this theorem, but a little history on good old Pierre de Fermat. All right, what Fermat's theorem here says, suppose that a f of c is a local extrema, a local maximum or a local minimum, then c must be a critical number of f. All right, so this says basically that if you have a local maximum or a local minimum, then the x value or that c value where that occurs is going to be a critical number. All right, so let's look at a couple examples. All right, find the critical numbers and local extrema of the following. And I've provided the graphs here for us. All right, let's do the calculus though. All right, according to Fermat's last theorem, we can find the critical numbers, which we can do by finding the derivative. In this case, this is 3x squared minus 6x minus 12. Glad I looked at that for a second because I messed it up. That's actually a what? 6x squared minus 6x minus 12. All right, and we set this equal to 0. All right, when we set it equal to 0, we notice on the left-hand side we could actually factor out a 6, which will leave me with x squared minus x minus 2. All right, and we've done this in an Algebra 2 class or advanced math class before. We factor that out. All right, we can factor that into, let's see, x and x. To get 2, it needs to be 2 and 1. And you get a negative 1 in the middle, so it needs to be a minus 2 and a plus 1. If we set both of those equal to 0, we get critical numbers at 2 and negative 1, which our graph seems to agree with. Okay, what happens at 2? we have a local minimum. What happens at -1? We have a local maximum. Okay, the next section we'll talk about, even if we didn't have a graph, how do we know it's going to be exactly like that? Okay, so critical numbers there. All right, let's look at B. Got a little cusp going on. It looks like it happens somewhere between 0 and -1, or -1 and 0. All right, let's do the calculus, see if we can figure that one out. All right, so the derivative looks like it's going to be a chain rule. So we got 2 over 3. All right, and then it'll be 3x plus 1 raised to the 1/3 power on the bottom, or -1/3 power. And we also need to take the derivative of the 3x, which would be 3. So we can either multiply it on the side or multiply it up top. Clean that up a little bit. This gives me 2 over 3x plus 1 to the 1/3 power, or the cube root of 3x plus 1 on the bottom. All right, now if we set this equal to 0, all right, nothing is going to make this 0. Okay, the derivative, notice there are no 0 tangents here. There's no 0 slopes going on. But we do know something happens right there. So if we set it equal to 0, the top's never going to be 0, so it's never going to be 0. But we can figure out where it's undefined, which according to the definition of critical number is also a critical number. So we set the bottom equal to 0 as well. All right, so we could say 3x plus 1 raised to the 1/3 power is equal to 0. To get rid of that 1/3 power, we can raise both sides to the 3rd power. That gives me 3x plus 1 is equal to 0. Subtract the 1, divide by 3. We have a critical number of -1/3. All right, notice it's undefined there, the derivative is, but it is a local minimum. All right, let's do the same thing with this one. Okay, if I were you at this point, I'd pause it and see if I could find it. All right, now that you're back, let's find the critical numbers. Again, we probably can tell by just looking at it, but let's do it anyway. So the derivative of x cubed is going to be 3x squared. All right, if we set that equal to 0, divide the 3 over, we get 0 is equal to x squared. Take the square root of 0, we have a critical number at 0. All right, because the function has a tangent line, the slope of 0 at 0. Is that a local extrema though? Is that a maximum or minimum? It's actually not, okay? This is not a high point. It's just like a stopping point before I keep on going up. All right, we can tell there's a tangent line of 0 there. We can see that there, but it's not a local extrema. Huh. Well, let's take a look at B. If I find the derivative of that, all right, using another power rule, this is going to be 1 over 3 times x to the 2/3 on bottom. And pretty easily we can say that, hey, nothing is going to make it 0. All right, because the top can't be 0. All right, but what will make the bottom 0? Well, I mean, there's a 3 and a 2/3 there, but there's an x. And so we also have a critical number here at 0. All right, and notice we have an undefined slope right there. Is that a maximum or minimum? Again, no. Okay, we got a vertical face there, but it keeps on going up. Okay, it's neither a high or a low point. All right, so at this point, a little important note. Looking back at Fermat's theorem. All right, it said, suppose that f of c is a local extrema, then c must be a critical number. Notice what it does not say. It does not say that a critical number guarantees a local extrema. It just says if there is a local extrema, it's going to happen at a critical number. Okay, so the critical numbers gives us a good idea of where they could occur, but it does not necessarily mean that does occur there, or local maximum or minimum occurs there. Okay? Not a guarantee, but it gives us good candidates for it, unlike our current candidates. All right, so let's look at this problem right here. We're not even talking about local extrema here. We're just going to talk about their critical numbers. So let's find the derivative. All right, it looks like it's going to be a quotient rule. All right, so we got low, which is x plus a 2, d high, which would be 4x, minus high, which is 2x squared, times d low, which is a boring one, all over x plus 2 squared. All right, we clean up the top a little bit. That would give us 4x squared plus 8x minus 2x squared. All right, and we combine like terms on the top, and we get 2x squared plus 8x over x plus 2 squared. That's our derivative. So if we want to find critical numbers, we need to figure out where's the derivative 0 or where is it undefined. Okay? The derivative is 0 when the top's 0. So 2x squared plus 8x equals 0. Do a little factoring. Factor out a 2x, which will give me x plus 4. All right, so that critical numbers where the derivative is 0 at, this x could be 0, and where this parentheses 0, which is negative 4. All right, and we can also find the critical numbers where the f prime of x, the derivative, is undefined. All right, and if we have a rational expression, we just set the bottom equal to 0. So we can pretty much see here really easily that what makes the bottom 0? Negative 2. So 0, negative 4, and negative 2 all give me what we think are critical numbers. All right, but let's go back and look at that definition of critical numbers again. All right, if the derivative is 0 or the derivative is undefined, but that c has to be in the domain of f. Okay, that means you actually get a value there. All right, so if you look at that one, if you're kind of familiar with rational expressions, since the bottom 0 of the regular function, we learned last year that there's probably going to be a vertical asymptote there. If we plug a negative 2 back in here, it's undefined in the original function. Okay? Now you could have a problem where you have a number undefined in the bottom, but not in the bottom of the derivative, and not in the function itself. But this is not one of those cases. It's actually undefined in both places. So negative 2 is actually not a critical number, okay, because it's not in the domain of the function. All right, I'm going to stop it right now. Second video will be about absolute extrema and how to find them.